In this video, we are going to be discussing the topics in Chapter 6, which include naming and writing the chemical formulas for ionic and molecular compounds. In addition, we are going to learn how to draw the Lewis dot structures for molecular compounds, followed by understanding attractive forces. The first thing that we need to understand is what makes an ionic compound and what makes a covalent compound. Understand that covalent compounds are also known as molecular compounds. So whenever you hear molecular compounds, then understand that that is another word for covalent compound. So as you can see in the following figure, ionic compounds are formed because we have the transfer of electrons between two elements. Specifically, when it comes to the elements that are involved in ionic compounds, we know that it's going to be a metal. That's what the capital M stand for. And we're going to have a non-metal. That's where the capital N followed by the small case m represents. Now, understand that the transfer of electrons between these two elements, it's always going to be, as you can see that I'm highlighting, from the metal to the non-metal. Always, always, always. What happens when that metal transfer an electron to a non-metal, depending on the number of electrons that are transferred, we're going to see that the non-metal is going to acquire a negative charge. Okay? Because remember that the non-metal is accepting electrons, and electrons are negatively charged. So then the metal, because it donated electrons, it becomes positive. Okay? And these two things are called ions. In a few minutes, we're actually going to name what those ions are specifically called. When it comes to a covalent bond, as you can see on the right side of the figure, it comes from the sharing of electrons, okay? But what kind of elements actually are sharing electrons to make a covalent compound or a molecular compound? They are going to be two or more non-metals, okay? And as you can see, the sharing of electrons, which I'm highlighting in purple, it doesn't look purple, it looks more brownish because of the yellow that is already in there. But those electrons that are shared, those are called a bonding pair. And those are the shared electrons between two or more, depending on how many you have, non-metals. Now, problem 1 in the worksheet that we have for the in class, it states that we have to determine if the following elements, when we combine them, are going to form an ionic compound or a covalent compound. So to do this, I'm specifically going to do the first 3 problems. Letter A, letter B, and letter C. So just make sure that you practice the rest at home or look at the answer key that will be posted on the Canvas site for the course. So if we look at these elements, the first thing that we have to determine, knowing where they're situated in the periodic table, is if they are metals or non-metals. So when it comes to this, oxygen, and I'm just going to use a shorthand just because of space, a non-metal is going to be Nm, while a metal is just going to be an M. So for the first pair, oxygen and chlorine. Oxygen is a non-metal. Chlorine is a nonmetal, so that means that when they combine, they're going to make a covalent compound. Okay? You can put the letter C also. In the next one, hydrogen and hydrogen. Hydrogen is a nonmetal. So when you combine two hydrogens, that makes also a covalent compound. Where we have magnesium and oxygen, magnesium is a metal, while oxygen is a nonmetal. So those two, when they combine, that makes an ionic compound. Okay, so you make sure that you practice the other ones. Now, the next thing that we're going to be focusing on is specifically in the formation of ionic compounds, because as I established already, those are the ones where there's going to be transfer of electrons. And transfer of electrons specifically form ions, okay? So remember, all of this has to do with ionic compounds. Now, when atoms form a positively charged, they are called a cation, okay? And a cation is going to be positively charged, okay? Because the loss of electron, that's where the positive charge comes from, okay? Now, where we have anions, that's where we have ions that are negatively charged, and that negative charge comes from the gaining of electrons that occurs in the system. So understand that having a cation and an anion is what forms an ionic compound. So overall, on the right side of the slide, we have an example of an ionic compound, okay? And as you can see, sodium formed a cation. Chlorine formed an anion. How do we know that? Well, I'm going to highlight it. As you can see, chlorine has a negative charge. Sodium has a positive charge. That's where I know which one is the cation, which one is the anion. Remember, ionic bonds are formed by the strong attractive forces between that positive and negative ion. So when it comes to an ionic compound, what is holding it together is going to be an electrostatic interaction that is happening between the two ions. Okay? Now, if we look more closely, why is it that cations and anions are formed? We're going to study it in more detail. So, when it comes to cations, understand that cations are made by metals. Okay? Because metals are the ones that are going to be losing electrons in the system. How many electrons does a particular element lose? Well, it depends on which group of the periodic table they're in. So, if we look at the metals in group 1A, 2A, and 3A, the metals in 1A are going to lose 1 electron. The metals in 2A are going to lose 2 electrons, and the metals in 3A will lose 3 electrons. Okay? Let me specify that for 3A specifically, the metals that we have there are going to be aluminum, gallium, and indium. Understand that boron, which is the first element in 3A, is not a metal. So this rule does not apply to boron. Now, if we look specifically of why is it that metals are going to be losing electrons, it has to do with electron configurations. Okay? So in order to study this, I'm going to first look at the electron configuration that it is present in ground state sodium versus sodium ion. Okay? So ground state sodium, understand that it has, as you can see in the first image, 11 electrons. Okay? If it has 11 electrons, then its electron configuration is going to be 1s2, 2s2, 2p6, 3s1. Okay? Now, when the ion is formed because of the loss of the valence electron, now sodium ion has 10 electrons. If we write its electron configuration, it's going to be 1s2, 2s2, 2p6. Now, if you ask yourself, okay, now that it lost an electron, what other atom actually shares the same configuration as sodium ion? Well, looking at the periodic table, you can notice that this all of a sudden looks like neon. Let me specify. Losing an electron for a specific metal, that doesn't mean that it is converted into a noble gas. No. This just means that it's going to have, because of the loss of an electron, a full valence shell, okay, like the noble gases. So what does that mean? Many elements, and in general is going to be your noble gases, because they have a full valence shell, they are actually very stable and they are hardly ever reactive. Okay, now everybody wants stability in this world, and that includes the elements in the periodic table. So for metals, that constitutes the losing of electrons, and those electrons are going to the nonmetals in order for them to gain a full valence shell and to gain stability. And again, whenever we have the loss of electrons for metals, we are forming cations. Remember that those electrons that are lost from the metals have to go somewhere. Where do they go? To the nonmetals. So remember, in this system, nonmetals are going to be gaining electrons. When you gain electrons, understand that that makes you more negative. That's what forms an anion. Okay? Now, when it comes to this, as I just established, nonmetals are the ones that are going to be gaining electrons. And you may ask yourself, but how many do they gain? Well, specifically the nonmetals that are going to be gaining the electrons are going to be located in 5A, 6A, and 7A. Okay? So, the nonmetals in 5A typically are going to be gaining 3 electrons. The ones in 2A are going to be gaining 2 electrons, and the ones in 7A are going to gain 1 electron. So see, 3, 2, 1. Now, what does this mean? That when we do the same exercise of looking at the electron configuration of a ground state nonmetal versus the anion that is formed, we will see what happens. So let's say that, for example, we take chlorine. So the chlorine atom, as you can see here, it has 17 electrons. If we do the electron configuration for the chlorine atom, it's going to be 1s2, 2s2, 2p6, 3s2, 3p5. Okay? Now, when we have the chloride ion, so understand that the name is different. When the nonmetal becomes an anion, we have a different name. So, when this chlorine gains an electron, now it's called the chloride ion. And now it has 18 electrons. If we write the electron configuration for that anion, it's going to be 1s2, 2s2, 2p6, 3s2, and 3p6. Okay? So, what happens all of a sudden? Once we gain that electron, now the chloride ion has the same electron configuration as argon. Similarly to what I explained in the previous slide, it is not that it becomes argon. What it means is that electronically it actually looks like, or at the level of electrons, I should say, at the level of the electrons, it actually looks like a noble gas. And in noble gases, again, they have full valence shells. So this is going to be the case of the reasoning, because the stability that is gained from either losing electrons or gaining electrons, that's why metals lose electrons and non-metals gain electrons. Now, the ionic charges for group numbers, as you can see, they're summarized in table 6.2 in the textbook, and this is just illustrating the same ideas that I showed before. So notice that all the non-metals in 7A have a charge of -1. The non-metals in 6A have a charge of -2. The non-metals in 5A have a charge of -3. Then when it comes to the metals, as you can see, the ones in 1A have a charge of +1. The ones in 2A have a charge of +2. The ones in 3A have a charge of +3. But remember that when it comes to this, even though aluminum is the only one that it is shown, gallium and indium are also part of that trend, and they're 3+. Now, it is important to know how to name cations and to name anions. One of the things that you can observe is that in this table, which this is table 6.1 in the textbook, is going to tell you how do we name cations and how do we name anions, okay? So for naming cations, understand that we're going to use the name of the element. So as you can see, for the lithium, when it comes to a cation, it's just going to be lithium ion. Sodium plus is going to be sodium ion. It's just that in the textbook, they don't write the word ion. Potassium ion. So that is the name, okay? I'm just going to erase it because when we actually learn how to name compounds, we're not going to include the word ion. But if we name anions, as you can see, they're going to have a separate way that we name them, which is we're going to have the stem name for the element, and you're going to add to it the suffix "ide." So as you can see, many of these anions, or in this case, all of these anions are going to have that IDE ending. Nitride, phosphide, oxide, sulfide, fluoride, chloride, bromide, and iodide. I suggest that you familiarize yourself with these names and even memorize them, because the more that you practice and the more familiar with the names, once we get to practice chemical formulas, it's going to be easier for you to identify what we are talking about. Now, the next thing that we're going to learn is how to write formulas for specifically ionic compounds. So when it comes to ionic compounds, remember, ionic compounds are going to be specifically where we have, so far, metals plus non-metals. And as we advance, we're going to see that ionic compounds are have about a diversity of 6 types of ionic compounds. But so far, we just have metal and non-metal. So again, in ionic compounds, we're going to have a positive and a negative charge. Remember that the positive charge is going to be from the metal. The negative charge is going to come from the non-metal. They're going to be held together by strong electrical attractions between the positively and the negatively charged ions. Now, remember that attraction is what is called an ionic bond. So there's not physically bond, there's not a line drawn, just the plus and the minus on the elements. In general, ionic compounds have high melting points and they tend to be solid at room temperature. That's why they're also known as salts. Now, when we're writing ionic formulas, understand that there is a process that we need to follow in order to accomplish this job. As you can see, the first thing that we're going to write is the symbol for the metal cation. And we have an example here on the right side of the slide, okay? So this ionic compound is going to be composed specifically of magnesium and chlorine, okay? So magnesium, okay, is going to be my metal. Its charge is 2 plus because it lives in 2A in the periodic table. Now, then we're going to write the symbol for the nonmetal and its charge. So in this case, remember that we have chlorine as my nonmetal. The charge is -1, but the number 1, the value of 1 in chemistry typically is omitted, so that's why you only see the negative charge. And that -1 comes from the idea that chlorine lives in group 7A. And everybody in 7A, as we see illustrated previously, has a charge of -1. Now, as you can see, the charge without the sign is going to become the subscript of the other ion. So let me just write them side by side. So if I have magnesium 2 plus and chlorine -1, okay, let me just write the -1. We are going to take the value. So let me just highlight it. I will take the value of 1, take the value of 2, okay? And I'm going to be making it the subscript of the neighbor. So what does that mean? That this number 1 is going to become the subscript of magnesium. This value of 2 is going to become the subscript of chlorine, okay? When that occurs, this is going to look like Mg1Cl2. But as I mentioned before, the value of 1 is omitted. So whenever you have a subscript of 1, you are going to erase it because it is known or assumed that it is there, but it is omitted. So that's why the chemical formula for magnesium chloride is MgCl2. Now, rule number 4 says that if we have a subscript that can be reduced to a whole number ratio, we will do so, okay? And we're going to see an example about that in the next slide. And then as number 5 is just a checkup, you can actually double check that your math is right by simply saying, as you can see in this area, let me just zoom in this area of the slide. If you know that we have 1 magnesium, if we multiply by the charge that it has, that's where we obtain this +2, okay? This value of 2 that you see here is because we have a Cl2 that is a charge of -1. So when we multiply that 2 by -1, that's where we get 2 of the chlorine minus. So because in an ionic compound, the charges are balanced, everything has to equal 0. That's how we know that MgCl2 is the correct formula for the compound magnesium chloride. So one of the things that we are going to be observing, and I'm going to be illustrating in this slide, I'm only going to be doing problems A, B, and I'm going to illustrate an example that is going to result in the reduction to a whole number ratio. So I'm just going to do an extra example here in the corner. So as you can see, for the first one, or the instructions read, write the chemical formula for the ionic compounds formed from each pair of elements or element and polyatomic ion. We haven't talked about the polyatomic ions, which is letters E through H. We will deal with those later. Now, understand that when it comes to these type of situations, we need to just take the name of the element and write the symbol. So for example, lithium, the symbol is Li. Because lithium lives in group 1A, is going to have a charge of +1. Bromine, the symbol is Br. Because it lives in group 7A, it has a charge of -1. As you can see, the +1 and the -1 are going to cancel each other. So the chemical formula for this compound is LiBr. Let's look at problem B. On problem B, as you can see, we have strontium. Strontium is Sr. Because it lives in group 2A of the periodic table, it has a charge of 2+. Iodine lives in group 7A, so it has a charge of -1. So in this case, we are going to move this value, and this is going to become the subscript of strontium. This number 2 is going to become the subscript of the iodine, okay? So in this chemical formula, this is going to be SrI2. It's not that I didn't do that on purpose for the first problem, for letter A. It's just that in letter A, since the charges already are going to be balancing each other because they have the same value, but they have opposite charge, then we don't have to actually exchange them. But if on paper you actually did Li1, Br1, and then you decided to write LiBr, you are correct, as long as you write LiBr as your final answer. Now, let me just show an example of something that specifically can illustrate rule number 4 that it was shown in the previous slide. Let's say that I have magnesium and sulfur making a compound, okay? So magnesium is going to be Mg, 2+, sulfur is 2, negative. So if I do the same example in which I take the value, not the sign, just the value, and I make it the subscript of the neighbor, then we can determine that the chemical formula is Mg2S2. But because the two are divisible by one another, if we divide, okay, the 2's by each other, then we can see that the chemical formula for this is going to be Mgs. So whenever you have 4 ionic compounds, let me just write a note about that. This is in ionic compounds. Okay, we have values that are divisible by one another, like 2. Can divide by 2, then we will do so, and we will be simplifying those subscripts. They're going to end as 1 and 1. But remember that the value of 1 is omitted, so that's why we need to erase it. And this is how you write the chemical formula for ionic compounds given the cation, the metal, and the anion, which is the non-metal.